So before I begin, I'd like to thank Fred Lowe, director of NRAO, and all the other his colleagues at the NRAO for giving me this award. I'm really flattered by it, and mainly because of the high esteem I hold the NRAO in. Some of my best memories of that I've had in my career have occurred during my interactions with people at the NRAO, some of who are in the audience tonight. Okay, so as Fred said, what I'm going to talk about tonight is research I've been doing probably the last 25 years now that has to do with the gas in galaxies, high redshift galaxies, protogalaxies, and in particular the cold neutral gas that we think makes stars. This work has been carried out mainly with various graduate students and collaborators distributed throughout various campuses at University of California, and Shoan Chen, who is a professor at the University of Chicago. Now, almost everything we know, at least most of what we know about high redshift galaxies comes from, I hope you can see this, this is the deepest image taken with the Hubble Space Telescope. It's called the Hubble Ultra Deep Field. For the astronomers here, the point source limit is about 30.5 magnitudes. It goes very, very deep. And for many years, up until very recently, astronomers were staring at images like this, trying to figure out which was the most distant galaxy. Clearly, it wasn't something like this, which has a redshift of about a half, look-back time, a few billion years. But they really wanted to find things way, way back in time. And the normal procedure was to go and look at the faintest objects. The idea was the fainter you go, the more distant a luminous galaxy would be. But that's not what happened. What people started analyzing images like this and finding out what the redshifts, the distance to these galaxies were. They tended to be intermediate redshift, low luminosity galaxies. That technique really didn't work. And it wasn't until about 10 years ago that Chuck Steidel at Caltech came up with a technique which was a major breakthrough. And he made use of the fact that most of these early type galaxies, not early type, but galaxies in an early phase, very early phase of the universe, would have young massive stars, and these stars would emit far ultraviolet radiation. Here's a spectrum of a young massive star in the far UV radiation. And these stars, of course, would form out of interstellar gas, and that was the idea he had. It seems kind of straightforward now, but nobody had thought about that before. And that radiation that would pass through this gas, which is optically thick, to ionizing radiation with photon energies greater than 1 Rydberg that would photoionize hydrogen. And so there would be almost nothing, okay, at wavelengths short within 912 angstroms. And the idea was then, if you take a star whose radiation passes through the interstellar medium and put it at a large redshift, say of a redshift of 3, then this absence of radiation, this break, would occur in the U-band. Okay, this is a U-band filter. What Steidel's idea was to image these galaxies with broadband filters. The broader the filter, the more energy you get, you can go much deeper. So instead of just taking an image through one filter, he took image through many filters. So U-band, ultraviolet band, a blue filter, and a red filter. And what he did is he compared red images with U images, and of course you'd expect there would be a very big color difference. And this led to a breakthrough. Again, ever since then, thousands of these galaxies have been found at very high redshift. And of course, this technique need not just be applied at a redshift of 3. You can go to higher redshifts where the Lyman break then gets redshift to blue wavelengths, on and all the way out to redshifts of 7. And here's sort of a rogues gallery of the type of galaxies that we find at these high redshifts. This is from the Hubble Ultra Deep Field from that image that I showed you before. These galaxies have redshifts of 4, and they don't look like galaxies that we see today. They're very compact. Okay? They typically have sizes about 1/5 the size of a galaxy today, about, say, 2 kiloparsecs. I mean, they have a lot of interesting characteristics. The two I'm going to talk about today is that they're very compact. They cover a very small fraction of the sky, about 1/1000th of the sky. That's one thing we're going to make use of. And secondly, they're very bright in far UV radiation. And far UV radiation, that the luminosity of a galaxy in this far ultraviolet radiation is proportional to the number of these young stars. And that's just proportional to the star formation rate times the age, the main sequence lifetime. So the brighter these objects are, the higher the star formation rate. So these have very high star formation rates, about 10, 20, 30 times what it is in the Milky Way, about 40 to 50 solar masses per year. And in fact, since Steidl's early discovery, people have really used this technique all the way out to redshift 6 using what's called Z-band dropouts, objects that are optically thick where there's no radiation at wavelengths, say, shorter than about 9,000 angstroms. And what people have been able to do is sort of trace the star formation history of the universe. And that's what the observed star formation, what's plotted here is the star formation rate per unit co-moving volume, per unit expanding coordinate volume as a function of redshift. And for the first time, we really know what the star formation history of the universe is. This is what's observed. It turns out Lyman break galaxies have a fair amount of dust. And you have to make a correction if you want to know the intrinsic star formation density. That's this higher curve. But really, I'm going to stick with the observed one because that's what I'm going to make use of today. And people have used this to learn about the production of metals throughout the history of the universe and things like this. Now, of course, this is only half the story because as you go far back in time, we know that most of the baryons in galaxies had to be gas. We know that stars form out of interstellar medium. And that's where we know very little. We know very little about how to find gas in galaxies. And one of the difficulties, especially cold gas, is that you cannot detect it in emission. The 21 centimeter line, the hyperfine transition in the ground state of hydrogen, is incredibly weak. It's one of the weakest emission lines we have. And until we build the square kilometer array, we just can't detect it in emission at high redshifts. So for this reason, in order to find this star-forming gas, what people have done is looked at the gas and absorption. So the idea is here is a very distant quasar, it could be a radio source in this case, or an optical source. A line of sight passes through this quasar to a telescope. Of course, I've chosen the appropriate telescope for this talk. And what happens as it passes through these clouds absorb, in this case, 21 centimeter line, okay? Because it's drawn like an optical line. But in this case, let's say wavelength goes to the right, frequency goes to the left. So this is a more distant cloud. It has a higher redshift. The wavelength is longer. Here's a galaxy over here. Here's a second absorption line, another 21 centimeter line, shorter wavelength. And over here, this might be a 40 centimeter line, a 30 centimeter line, and finally gets down here. And so the idea, of course, is the line is as strong as the quasar is bright. I have an optically thick line, I have a very bright quasar. The line depth, okay, we can detect the absorption lines with exquisite accuracy. But it turns out that most of the absorption lines that, and I'll show this in a minute, that people found by these techniques, especially optical techniques, arise in gas that's mainly ionized. I haven't been interested in that. What I was interested in is the cold neutral gas that ultimately gives rise to the molecular clouds that then form the stars. Now, the first detection of this cold gas was made by someone in this audience, Mort Roberts and Bob Brown, a very long time ago, like 35 years ago, using the old 300-foot, which doesn't exist anymore. And what they found was a 21 centimeter absorption line at a redshift of 0.692. And I remember when they found this many, many years ago, I became very interested in this because it turns out because of all the physics of the 21 centimeter line, it turns out that the strength of this absorption line is not only proportional to how many hydrogen atoms you have along line of sight, it's inversely proportional to the temperature of the gas. The colder the gas, the stronger the line. So that was very intriguing. I got very interested in this, and so I started turning my research in this direction, and I went to Arecibo and started looking at these 21 centimeter absorption lines. Of course, Arecibo has tremendous singleton noise. Here's another 21 centimeter absorber that was found at Green Bank by Mort and Bob Brown, and I was involved in this. And this is an Arecibo spectrum of it. And see what it is, they're multi-component. There are several clouds in absorption. This is a redshift about 0.524. Here's another one that was found later, higher redshift, and this one, even higher redshift. You can see this is a very strong 21 centimeter line. These were all found at Arecibo. This one was found, my colleagues and I found these, and Nissim Kanekar and his colleagues found these very recently. And they're very interesting for probing cold neutral gas, but the problem is that they're few and far in between. They're great for getting a lot of physics okay, physical knowledge of the absorbing gas, but they're not great for doing surveys. And this is one reason why I turned my attention to optical astronomy, okay, because here is the optical spectrum of a quasar that my colleagues and I obtained at the Keck telescope with very high resolution. This is Lyman alpha emission, and you can see at wavelengths short of Lyman alpha emission, you have these enormous number of absorption lines. And I should say the 21 centimeter line is a magnetic dipole transition. It's highly forbidden. It's very weak. Lyman alpha, of course, is an electric dipole transition. It's very strong. It's almost too strong for what we want to do. Now, of course, with this wonderful spectrum, okay, we can tell the very strong lines that I'm very interested in. This is called a damped Lyman alpha absorption line, and because this arises in a gas, neutral gas with a column density of about 10 to the 21. But before we had such exquisite resolution, it was hard to distinguish something like this from these so-called Lyman alpha forest lines. These are thousands of absorption lines. They occur at high redshifts, lower and lower and lower. Okay, they're all Lyman alpha from intergalactic clouds along the line of sight. Some people make a living out of the Lyman alpha forest. For me, they're a pain in the neck. They're a source of confusion noise. Okay, and that was one of the difficulties we had originally. But nonetheless, the advantage is that you can see with a typical optical spectrum, you get a wide redshift coverage in a single spectrum. And again, most optical quasars are radio faint, so you have a lot more quasars, you get a lot more statistics this way. As I said, the disadvantage of working with optical surveys is that the confusion noise of the Lyman alpha forest. But as I said, these damp Lyman alpha lines, okay, they arise in the same neutral gas that causes 21 centimeter absorption, and that's how I became interested in this. So what I'm going to do today is talk about some of these optical surveys for neutral gas at high redshift. I'm going to talk about what we've learned about the efficiency of star formation in these damp Lyman alpha systems. I'll call them DLAs. And then I'm going to talk about some investigations that I've been doing at Keck on the metal absorption lines, what we learned about bimodality in these damp Lyman alpha systems. And I'm going to end the talk about a very recent radio astronomy investigation that we carried out with the GBT, which resulted in the first actual measurement of a magnetic field outside the Milky Way. It sounds amazing, but it's true. And then I'll give some concluding remarks. So let me first start talking about damp Lyman alpha surveys. Now, this was revolutionized recently, mainly by my colleague Jason Prochaska, came up with a very interesting way to analyze the data. This is sort of a rogues gallery of 720 damp Lyman alpha profiles. In fact, we have about 1,500 of these now. Before we started this is from the Sloan Digital Sky Survey, which is one of the best things that's happened in optical astronomy. And we now have statistics of about 1,500 of these. So we really, for the first time, have robust statistics about neutral gas at high redshift. And one of the most interesting statistics that we obtained from this is called the frequency distribution of column densities. And if I just take the column density weighted average of this integral, I get what's known as the H1 co-moving density of neutral hydrogen. And that's shown over here. Okay, this is a very recent result that we have. And what this shows is that for the first time we've really been able to demonstrate that the neutral gas content, the neutral mass density of the universe is decreasing as we go forward in time. Starting out at a time the universe was about 2 or 3 billion years old, and ending over here when it's about another 1.5 billion years older. So there's a significant decrease until you hit this at a redshift of 2. It hits this value, and it's interesting. This is the value that we see today. Okay, that the neutral gas content of the universe is at most changed by a factor of 2 during the last 10 billion years. So I think this is what's led to the idea that what we are looking at is neutral gas reservoirs. Schematically, remember, galaxies are not a closed box. Okay, they're accreting gas from the interstellar medium into this reservoir, some bathtub, okay? And that's the input. The output is star formation. Gas is being consumed, okay, by star formation. And the balance between these two effects, okay, gives rise to a certain level of neutral gas, okay? And as I said before, the stellar content that we see in galaxies is about a factor of 2 more than the neutral gas content. But nonetheless, it's widely agreed that the damp Lyman alpha systems are significant neutral gas reservoirs for star formation in high redshift galaxies. So let me just summarize this by saying one of the things we found is that in this redshift interval, 2.5 to 3.5, the area covering factor, the DLAs cover 1/3 the sky. Okay, a very significant fraction of the sky. That's something we didn't know before our survey. And this is in stark contrast to the galaxies that are forming stars at a rapid rate, the Lyman break galaxies, which only fill about 1/1000th of the sky. And as I said, this is their co-moving star formation rate. They're forming stars at a very high rate. So this disparity interested me, and so several years ago, my colleague Xiaowen Chen and I said, well, if there's so much gas throughout the universe, this cold neutral gas, it's probably forming stars. And if that's the case, then a significant fraction of the universe should be covered with starlight, very faint starlight. We went out to look for it, okay, using that image that I showed at the beginning of the talk, the Hubble ultra deep field, okay? And so this is a blow-up of some of these images. For example, this is the Hubble ultra deep field in a wavelength of 8,500 angstroms, what's called the Z band. This is a shorter wavelength, the I band, the visual band, the blue band. And I don't know if you can see it, there's a very faint smudge. I hope you can see it. This is the kind of things we were looking for. Low surface brightness extended objects. And to optimize, okay, the signal to noise of detecting these objects, we use what's called a smooth matched kernel technique. We smooth the data with a smoothing kernel. We just went through with a filter whose size was matched to the size we expected these objects to be. And we did it for a whole range of smoothing kernels. And you can see how well that technique works. You can hardly see it in the unsmoothed data. The signal noise really pops out. And this is a very, very faint object. It has a surface brightness of 28 magnitudes per square second, a very faint magnitude. So if these faint things are there, we're going to find them. But we found hardly any at all. That was the big surprise. The number we found was something like 1% of what we expected. And to make a long story short, we were able to put, as I said, the luminosity of these objects is proportional to the star formation rate. We were able to put an upper limit on the co-moving star formation density due to in situ star formation that occurs throughout the gas, significantly lower than what we see in the Lyman break galaxy. So again, this was an interesting fact. I'm not sure we know what it means yet, but clearly that stars are forming at very low efficiency in most of the gas of the universe at high redshifts. Oh. Okay, so now I'm going to make use of that upper limit in a few minutes. Now I want to turn my attention to the meta lines. I should have said this before. Every damp Lyman alpha system that we look at doesn't just have neutral hydrogen, it has all the abundant elements in it. And one of the nice things about these systems, they're very neutral. We know the ionization state very well, and we can determine the metallicities to very, very high accuracies. These are the most accurate metal abundances that we know. And the way we do that, we take, these are from the Shell spectrometer on Keck called high-res. These are velocity profiles in these various elements that we see, in singly ionized elements, because they're the elements that are associated with the neutral gas. Iron, can't see it from here, I think that's chromium, or coal, I don't know. Nickel, silicon, carbon, okay? And we use these things for different purposes. This is, we get the abundance of the heavy elements from the silicon lines. It's not very depleted, but it turns out for iron in the interstellar medium, we know is depleted onto dust grains. And we know that there is dust in these objects because we see these depletion patterns. So we can learn something about dust from them. From the line width, from the total velocity interval, we can construct what's called the velocity interval measure. Okay, we just measured by the velocity interval over which about 90% of that line strength occurs. But what I'm going to focus on right now, these are all resonance lines. These lines all arise from the ground state. I'm going to focus on this line over here. This is called a carbon-2 star, because this line arises from an excited fine structure state. Okay, and here's the atomic energy level diagram. This line is actually a doublet that arises from this 2p3 half state, goes up to these states over here. It's 1335.7 angstrom. Why is this line interesting? It's interesting because spontaneous emission from this state down to this state gives rise to this photon with a wavelength of 158 microns. And those of you who know something about the interstellar medium know that this is the dominant coolant of the interstellar medium of the Milky Way. For example, the Kobe satellite in 1991, when it surveyed the plane of the Milky Way, this line was 1,000 times stronger than all the carbon monoxide lines put together. It's the way gas cools, the way atomic gas cools. So it's interesting. Of course, ultimately, we would like to see this line in emission with ALMA, hint, hint. But it turns out we don't have to wait for ALMA. We can learn a lot about this already, because by measuring this transition in absorption, we can get the column density of carbon, singly ionized carbon in this excited fine structure state. We know the H1 column density, okay, we divide by that. We know the energy of this transition, the Einstein A coefficient, and that tells us the cooling rate per atom, okay? Without just UV spectroscopy, we can learn about how this gas is cooling. And it turns out the cooling times, when you work it out, are very short. They're about 1 million years or less, which is short in astrophysics. And what this tells us probably is that by measuring the cooling rate, we can determine the heating rate. The gas is probably in a state of thermal balance. So for the last 5 years, we've been doing this at Keck. We've measured this transition of about 84 damped Lyman alpha systems. And what I'm plotting here is this cooling rate per atom versus the H1 column density. The red are positive detections. The green are upper limits. These blue guys here are lower limits. Here's an average for the Milky Way. So these rates are much lower than the Milky Way, but we think we understand why that is. But what I want to emphasize here is you just look at these positive detections. They occur in 2 clumps, okay? And this is the first hint that there's a bimodality. And when you take a histogram, there really is evidence for 2 types of DLAs. This is the histogram of these cooling rates. And this bimodality has existed. It just doesn't go away as we keep adding more and more systems. There's a trough over here at some critical cooling rate, about, in these units, I'm plotting against log of the cooling rate per atom. It occurs at about 10 to the minus 27 in these units. And we have 2 classes of DLAs on either side of these, okay? And so if this distribution really is bimodal, okay, what this means is that the physical properties of these, what I call the low-cooled DLAs, should be physically distinct from the high-cooled DLAs. And the question is, are they distinct? And the answer is yes. Because what I'm plotting here, for example, I'm plotting these line widths that I talked about before, these velocity intervals. The blue are the low-cooled DLAs. The magenta are the high-cooled DLAs. It's clear that the magentas have higher cooling rates than the low-cooled DLAs. And here, for those of you who are statistical fanatics, this is the cumulative distribution, and the probability that these 2 guys come from the same parent population is tiny. It's 2.7 times 10 to the minus 5th in a Kolmogorov-Smirnov test. So they really have different velocity intervals. So this is one piece of evidence that they're distinct. The same is true with the metal abundance. This is the log of the metal abundance with respect to solar. So 0 is solar abundance, minus 1 is 10%, minus 2 is 1%. So the first thing, all damped Lyman alpha systems have subsolar abundances. There's a floor at 10 to the minus 3. We could easily see 10 to the minus 4, 10 to the minus 5. We never see that. That's interesting in itself. But again, the high-cooled DLAs have certainly higher metal abundances than the low-cooled DLAs. The probability that they come from the same parent population is vanishingly small. We could also calculate the dust-to-gas ratio. This is somewhat model-dependent by looking at the depletion patterns. There's iron and elements like iron and chromium occur at abundances with respect to the sun much lower than undepleted elements like silicon. But again, not surprisingly, the dust-to-gas ratios with respect to the Milky Way are a lot higher in the high-cooled DLAs and the low-cooled DLAs. And one other statistic that's very interesting for us is the silicon-2 equivalent width. This is a measure of the strength of this silicon-2 line. Why is this interesting? It's interesting because this line is always black. It's always saturated. And the strength of the line tells us nothing about how many atoms there are. It turns out the strength of the line tells us about the velocity dispersion of the gas. And silicon-2, singly ionized silicon, can occur in not just neutral clouds, but in photoionized clouds, okay? And so what we think, these are clouds all over the galaxy, not just the neutral gas disk. And what this is really telling us, this velocity, the strength of this line tells us about the velocity dispersion due to the entire dark matter halo enclosing the disk of this galaxy. But interestingly, the H1 column density distributions, the number of H1 atoms along the line of sight, in the two populations are indistinguishable. And the reason we think this is very interesting is because originally we thought, well, maybe these low-cooled DLAs are lying in the suburbs of the high-cooled DLAs. So the outer regions, we know that galaxies have negative metallicity gradients. As you go out in radius of the galaxy, the metallicities are getting lower. When you work it out, you send a line of sight through the outer regions of a rotating galaxy, the line widths are getting lower. But then you'd expect that the H1, the neutral hydrogen column densities would be lower on the outskirts, and they're not. They're indistinguishable. So for this reason, we think we're looking at two parallel sequences, okay, which have distinct properties. They're really not different aspects of the same object. All right, so we can learn a lot about these things. So one thing is the total, what I call the global energy budget. So, for example, for each population here, I'm plotting what's called the co-moving cooling rate and heating rate versus the cooling rate per atom. And I've just plotted the averages for the low cool versus the averages for the high cool. The co-moving cooling rate, we know how much cooling rate there is per atom. We know how many atoms there are per unit volume. Therefore, we know the cooling rate per unit co-moving volume. And so, for example, for the low cool DLAs, here's the cooling rate, the global co-moving cooling rate. We can compare that with what we think is the heating rate. Okay, the gas is heated, as I said, by, well, maybe I didn't say this, but the gas is heated by the same mechanism that heats the neutral gas in our galaxy. It's called the grain photoelectric effect. When ultraviolet photons hit dust grains, these little solid-state particles, they eject photoelectrons. Those electrons undergo Coulomb interactions with the ambient electrons, and that's how they heat the gas. Okay, and it turns out that that heating rate is proportional to the luminosity density, how many photons per second are emitted per co-moving volume. Okay, and that's proportional to the star formation rate per unit volume. And remember before I showed you that there was an upper limit that Chen and I placed on the star formation rate per unit co-moving volume. So we can put an upper limit, okay, on the heating rate per unit co-moving volume, and it's significantly above the cooling rate. So we think in this case, okay, in situ star formation in damp Lyman alpha systems, in the low cool population, even though it's fairly low, it's certainly lower than the Milky Way, okay, it's still consistent with this gas being heated by in situ star formation rate. It's enough to power. But that's not true for the high cool population. Here, the cooling rate is much higher, and it's significantly higher than the upper limit to the heating rate. So there's not enough energy coming out in star formation, in situ star formation, to heat the gas in these high cool DLAs. So we need an external source of energy. And our speculation, and we think we have a lot of good arguments for it, that in these high cool DLAs, what's really going on is that embedded inside them are Lyman break galaxies, these very bright cores. Far UV radiation leaks out from these cores and heats the gas surrounding them. And it turns out when you look at this quantitatively, it works out, okay, because that heating rate will be proportional to the co-moving star formation rate of Lyman break galaxies, which we know very well. And again, when I say we know it we do know that very well, but the heating rate, there are some statistical uncertainties, but nonetheless, it's consistent with that these Lyman break galaxies can balance the cooling rate that we see in the high cool DLAs. And it's further evidence, my student Jeff Cookie many years ago did an analysis of the cross-correlation function between damp Lyman alpha systems and Lyman break galaxies. He imaged fields containing damp Lyman alpha systems, looked for Lyman break galaxies, and he found that the number of objects, a number of Lyman break galaxies that were there, were significantly higher than any random point in the sky. Okay, and it turns out what I'm plotting here, the blue is what's called the two-point correlation function for Lyman break galaxies by themselves. The red is the cross-correlation function between Lyman break galaxies and damp Lyman alpha systems, and they're indistinguishable. And so the most straightforward explanation is that they're the same objects, at least some fraction of them are. And we can go on and on about that, but I'm not going to do that right now. There's a lot of other interesting. So we think that there are two classes of objects, okay? These are the high cool DLAs and the low cool DLAs for the reasons that I've said before. Okay, they have lower velocity widths, lower metallicities. The heavy odds are these are lower mass galaxies. These are the high cool DLAs are high mass galaxies. And this fits in very well with models, in particular model that the bimodality of Avishai Deckel and his colleagues, and their idea is that there's a transition in the way gas accretes onto galaxies, and their idea is above a critical mass of a few times 10 to the 11th solar masses, gas accretes from the intergalactic medium, gets heated up to the virial temperature, to the equilibrium temperature of the galaxy, about 10 million degrees. Okay, and that gas clearly cannot form stars, but because of the cold dark matter model, there are cold dark matter streams going into the galaxy, and they funnel in cold gas. So their idea is that the neutral gas that comes in, we've talked a lot about this neutral gas that accretes along the filaments could give rise to these damped Lyman alpha systems. The neutral gas columns, when they come in, their idea is they collide at the center, and this gives rise to these star-forming bulges. On the other hand, the low cool DLAs, the gas never gets up to the virial temperature of the dark matter halo surrounding this thing, and we just get neutral gas disks with a very low star formation rate. And so I think maybe what we're seeing is the origin of the bimodality that we see today in galaxies. Today in galaxies, this is just like stars. Galaxies have a color magnitude diagram, red going up, blue going down, and the way this is configured, stellar mass goes to the left. So these are the high mass galaxies, which we think originate in the high cool DLAs, and these are the low mass late type galaxies that come from the low cool DLAs. Okay. So at least right now, this is what we're pursuing, that we think we are really looking at the origin of this. Of course, one test of this would be to go and see the high cool DLAs in emission, and in particular, the 158 micron line. This is an image of a nearby galaxy in the 158 micron line. And the really interesting thing about this is superimposed on a 5 micron image, which really shows where the young stars, the hot stars are. And you can see we can really, these contours tell us where the 158 micron line is. And it shows where the cold gas is and how extended it is. And of course, we would love to do this at high redshift. And of course, looking at the kinematics of the gas, you can learn about the mass of the system that's holding it together. People have tried this before with damped Lyman alpha systems and failed, but we think we have a better chance because here, again, I'm showing this bimodal distribution of cooling rates. I've now included the lower limits. And remember, these high cool DLAs are the more massive ones. They're going to have, not only do we know the cooling rate per atom, we can guess at least and estimate how many atoms there are. And our favorite object is this one. This is the highest cooling rate per atom. And really what we'd like to do is use ALMA or whatever telescope we can get our hands on and look for this object in emission because it's the highest cooling rate per atom in the 158 micron range. And because of all the characteristics, we think it's a massive object. And here is our estimate of what I'm plotting here is the flux density of some of the DLAs versus redshift. This is the ALMA 3 sigma sensitivity after 20 hours of integration over some velocity width of about 100 kilometers a second. You can see how difficult it is. There are these redshift deserts in ALMA where the sky is completely blocked out. And even when you can see it, the noise level is not so great. But when you get to about a redshift of 4 or higher, there's a possibility. And here's this object that we really eventually want to go after. And hopefully we can learn more about that, about how bimodality in galaxies originates. Okay, so what I'm going to do now is, for the final part of the talk, is switch gears completely. And I'm going to talk about another aspect of the interstellar medium which has been ignored, and that's magnetic fields. Of course, all galaxies today have magnetic fields, or at least all late-type galaxies have magnetic fields that we know about. And that means we look at the progenitors of galaxies, which we think the damped Lyman alpha systems are. Perhaps they should have some magnetic fields too. What do we know about magnetic fields in galaxies? Well, in nearby galaxies, we know about them from emission. It's mainly synchrotron emission, relativistic particles spiraling around in magnetic fields. And here's an image of a galaxy, famous galaxy M51. These are I think this is 11 centimeter map. These are contours. The arrows are the directions from the polarized emission where the magnetic fields are. You can see what we know about galaxies, magnetic fields in galaxies, is to have a large scale coherence length. The magnetic fields are organized on incredibly large, they're coherent on scales of 10 kiloparsecs or more. And using equipartition arguments, because we don't know exactly what the strength of these magnetic fields are, so we have to make assumptions. And the usual assumption, which is reasonable probably in most cases, is that the magnetic energy density is equal to the energy density in cosmic rays. And the typical magnetic field throughout most of these galaxies comes out to be, throughout most the regions of these galaxies, comes out to be about 5 microgauss. Locally, in absorption, okay, in the Milky Way, we can learn about the magnetic fields, and I'm going to talk a lot about that in a minute, in neutral clouds from Zeeman splitting of the 21 centimeter absorption lines. Magnetic fields are very significant in galaxies, and this is from a work by Rainer Beck and his colleagues, where he plots the energy density in magnetic fields and in turbulent motions, and they're comparable. In fact, the magnetic fields even dominate. So really, the motions in the interstellar medium are really influenced by magnetic fields. And of course, there's a lot of debate in the community, in the star formation community, but I think most people would agree that magnetic fields can suppress gravitational collapse in a local cloud if the magnetic pressure is comparable to the weight of the gas. Okay, and when it's greater than or equal, these are called subcritical clouds. When the magnetic pressure is less than the weight of the gas, these are supercritical clouds. And a figure of merit is that for an H1 column density of 10 to the 21 particles per square centimeter, if the magnetic field is greater than 3.5 microgauss, that cloud is going to be subcritical, it won't collapse. Okay, so these are these 21 centimeter lines that I showed you before. Carl Hylas, Tim Robichaud, Regina Jorgensen, and I went out to the GBT about a year ago, I guess it is now, looking for Zeeman splitting in the 21 centimeter absorption line. These are the two objects that we looked at. This is the one that I said Mort found many years ago. This is a much higher singleton noise spectrum. It's almost a perfect Gaussian. It's incredible. Okay, and 3C 286. We also tried this one, but we got killed by interference. Why do we look at these two features? Well, it's because the line depths are very strong. Okay, in units 10 to minus 26 watts per square centimeter, I can't remember, is 1 Jansky. So this is a very strong line, about 1 Jansky, but this guy is even stronger, almost 2 Janskys in line depth. In addition, the lines are very narrow, and that's critical for Zeeman splitting. Okay, so for those of you who may not be familiar with this, let me say a little bit about it. This is an energy level diagram of the ground state of hydrogen due to hyperfine interactions. There's a ground state singlet and a ground state triplet. When I turn on the magnetic field, the degeneracy of that triplet is removed. Okay, and so the energy is proportional to the magnetic eigenvalue, to the projection of the angular momentum vector along the magnetic field. Whether it's along the magnetic field, it's higher. When it has zero projection, it's over here. And when it's anti-parallel, when the angular momentum vector is anti-parallel to the magnetic field, then the energy is a little bit lower. So to do this experiment, we have to use circular polarization. Okay, why is that? Okay, it turns out that a photon in a state of circular polarization, that state is an eigenstate of the spin angular momentum vector. Okay, spin angular momentum operator. And it has eigenvalues plus h bar for right circularized polarized photons and minus h bar for left circularized polarized photons. So for a photon, I'm just going to consider the case of a photon moving in the direction of the magnetic field. That's the simplest case to think about. So a right circularized photon can only excite this MF equal +1 state, and a left circularized a photon in a state of left circular polarization can only excite this MF equal 1 state, because here the photon spin is anti-parallel to its direction. Okay, it has spin angular momentum minus h bar, so it can only excite this state to conserve angular momentum of minus h bar. And of course, it gets a little more complicated when the magnetic field is at an angle with respect to line of sight, but this is the basic physics. So what this means, okay, is that the optical depth profile, what I'm plotting here is the optical depth in the 21 centimeter line as a function of frequency minus the frequency at line center in units of Doppler width. So because of the splitting, there's basically two profiles. The right circularized photon sees this optical depth profile. The left sees that blue one over here. I've exaggerated the splitting Even the great spectral resolution at the GBT cannot resolve these lines. I mean, they're split hardly at all. But what's interesting, if I take the difference between these two, okay, that I can measure, and this is proportional. The difference between these optical depths is proportional to what's called the V Stokes parameter, which is the intensity in right-hand circularized photons minus left-hand circularly polarized photons, okay? And the interesting point is that the difference, where there's these differences, the Stokes V parameter, where it hits a maximum and a minimum, that occurs about 1/2 of a Doppler width away from line center. That's independent of the splitting. So we can really measure this difference. So a signature of a magnetic field is in Stokes V. We should see this S curve, okay? So we went out in 3C286, and this is what we found. This is for what Stokes I is, just the ordinary intensity profile. So we were able to reproduce what we had found at Arecibo many years ago. But here's Stokes V. And you can see you have this statistically significant S curve over here, which is signature of the magnetic field. The shocking thing is the strength of that magnetic field. Okay, well, let me just backtrack for a minute. So we were able to reproduce. We now know the redshift to incredibly high accuracy. Notice how narrow. This is a Gaussian function with a dispersion of only 3.75 kilometers a second. This is really quiescent gas. The optical depth is about 1/10. But what blew us away is the magnetic field. As I said before, the typical interstellar magnetic fields in most galaxies is on the order of 5 to 10 microgauss. Here, the line of sight component is 84 microgauss. So it's completely unexpected. It's unexpected because all the models for magnetic field generation predict as you go back in time, magnetic field should be weaker in the past, not stronger. And here we go back in time, we find a magnetic field is stronger. The truth is we sat on this data for a half a year because we thought we'd never detect anything. And then finally someone decided to reduce the data, and this is what we found. Okay, so there's another interesting aspect of this, and this has to do with an experiment that Jim Condon, John Broderick, and Ken Johnston and I did a number of years ago. This is a map of the background radio source of 3C286. This is closest to the frequency where we had 21 centimeter absorption. We detected 21 centimeter absorption at 839 megahertz. And so the source has a core jet, there's an unresolved core, and it has a jet. Extends out about, I can't see it from here, about 0.02, 0.03 arc seconds. And here is a cut along the jet, and just look at the dotted profile. So the jet has about 2/3 of the flux, and the core has about 1/3. And it's almost 35 years ago, I guess it was, when we did this experiment at Arecibo, and we found by looking at the fringe amplitude and phase shift spectrum that the gas, the 21 centimeter absorbing gas, has to extend across the entire radio source. So what we're doing here is we're looking at a 21 centimeter absorption, not by a single cloud. When you do an experiment in the Milky Way in 21 centimeter absorption, the beam just goes through one interstellar clouds. But here at a redshift of 0.7, the beam is giant, okay? And the beam, if this object that we're looking at, this galaxy in absorption, is anything like the Milky Way, we're seeing hundreds, probably thousands of clouds in absorption. That's probably why it's such a perfect Gaussian from the central limit theorem. When you add up many different random motions of clouds, you'll get something like a Gaussian distribution. And we can't prove it yet, but it's very likely that the magnetic field coherence length goes right across here. It would be very unusual if the magnetic field was just confined over here. And of course, if you confine the magnetic field to a small area coming factor, it has to even be bigger than 84 microgauss, because there would be a tremendous imbalance of pressure, and that would drive motions right across here. What Jim Condon and I found many years ago is that the velocity centroid of the gas doesn't shift by more than a few kilometers a second across that. So the most likely thing is that the magnetic field is coherent across that dimension. Now we have a lot of information about this object. Here is a damped Lyman alpha system that Jacqueline Bergeron and her colleagues found using the space telescope. It has a column density very large, about 2 times 10 to the 21. And then we got Keck data on it, and it's very unexciting. All these lines are unresolved. It's incredibly narrow, which is what was indicated from the radio spectrum. We see iron, chromium, zinc, and silicon, and all the lines, they're slightly resolved, but hardly at all. Interestingly, this is the velocity central of the 21 centimeter line. It differs from that of the optical line by only 3.8 kilometers a second. Those of you interested in changing physical constants can take that away. The line velocity dispersion is probably lower than that of the 21 centimeter line. And that's because the optical beam is probably a light year in diameter, not 600 light years in diameter. So we're going through a subset of clouds. But what was so interesting is the metal abundance is very low. It's about 1/20th of the abundance of the sun. So that indicates this is not a star-forming region. This is not the kind of region where we see synchrotron emission from magnetic fields in nearby galaxies. This is a region with a very low metallicity. And it also has, not surprisingly, a small amount of dust, 1% the galactic value. I don't have it here, but there's a faint object spectrograph spectrum where we looked for this interesting line that I've been interested in, the cooling line. And it turns out the cooling rate from this object is about 1% of what it is in the Milky Way, okay? And I can go back and determine that the heating rate is lower, and then from that we can determine that the star formation rate per unit area is about a factor of 3 lower than it is in the Milky Way. So all the indications are you have a giant magnetic field and an object that's not forming stars hardly at all. And that's something new. Okay, so what about some of the physics of this object? Well, as I said, the magnetic field, remember, we just measured a line of sight component. For any reasonable projection, say that the magnetic field is lined up in a plane parallel object, the magnetic pressure is enormous compared to the turbulent pressure. So this, due to random motions in this object. So this object is not an equipartition at all, not like some of the galaxies that I showed you before. The magnetic pressure is enormous, or the magnetic energy density is enormous compared to the random kinetic energy density. So what we considered was the magnetostatic equilibrium of this object. Let's just say we have a plane parallel layer with a magnetic field parallel to the plane, and the magnetic field changes in the direction perpendicular to the plane, but it's sort of uniform within the plane. And what you can show is that in equilibrium, the pressure at midplane is equal to the weight of the gas above. Sigma, capital sigma, is the mass surface density perpendicular to the plane. And you can show easily that for many random inclination angles, the minimum value, so this is what's predicted if you have magnetostatic equilibrium, the minimum value is a factor of 700 times that, okay? So there's no way that this magnetized gas, it cannot be confined by its own self-gravity. There's just too much pressure from below. The weight of the gas cannot confine it. So one possible explanation is that this is an equilibrium configuration and that the extra gravity is supplied by the mass of stars, that there are stars associated with this gas. Remember, they can't be young stars because you don't see much star formation. They have to be an old stellar population. And it turns out they have to have a surface density of about 350 solar masses per square parsec. Remember, in the solar neighborhood where we live, it's about 50, okay? But 350 is no big deal toward the centers of toward the center of our own, in the Milky Way, there are surface densities that high. And surface densities like this have been seen in the centers of galaxies. So that's one possibility. So here is an object that, again, Reiner Beck found in synchrotron emission. This is the center of a barred spiral galaxy where they found that the equipartition magnetic field, where, again, the magnetic energy density equaled the energy density in cosmic rays, they came out with 100 microgauss, so it's somewhat like that. But this is because they see it in synchrotron emission. There's a lot of molecular clouds here. This is a very intense star-forming object. So I don't think this is the kind of object we're looking at. I don't think we're looking at the central regions of a barred spiral. But then another possibility is that it turns out that early type galaxies like S0 or elliptical galaxies, these are galaxies that are not forming stars, a significant fraction of them have H1 disks, okay? Interestingly, here's just one example. The axis of the H1 disk is very different than that of the starlight. And the speculation is that these disks have been acquired by some merger event, okay? And it's possible because we know nothing about the B fields in these objects because there's a selection effect. The way we usually find B fields is by looking at synchrotron emission. And these have only old stars, so we're not going to see synchrotron emission, but we can't rule out the presence of a magnetic field. So it's possible that's what's going on. There's an old population of stars which has a surface density high enough to confine the magnetic field. Perhaps we're looking at an object like that. Okay, is there any evidence for foreground galaxies? And I hope you can see this. This is an HST, a space telescope image, again found by the French group in '97 and re-reduced by Chen very recently. This is what's happened here. The quasar used to be here. She subtracted out the quasar, and this black stuff is the light, the residual emission from the foreground galaxy. And notice that it's asymmetrically distributed with respect to the quasar. So this is consistent, okay, with the foreground galaxy, with a line of sight from the quasar coming out to the central region. From here to here is only a few kiloparsecs. Okay, it's the central regions of a galaxy. Okay, so that's a possibility. And I hope you can see that, but there's a little thing over here that turns out is statistically significant. And I put a little red thing around here so you can see it better. That object, it's faint, but it's there. This little filament has a magnitude of 23.6 magnitudes. And the question, what is that thing? It's a filament. Is it the outer spiral arm of this galaxy? And it's interesting that the reason we think this is, another reason why we think it's real, is statistically significant in this image. And many years ago, Steidel and Pettini and their colleagues with a ground-based image, I don't know how they did this, subtracted out the quasar and said there was a galaxy right in that place. So there's two pieces of evidence suggesting it. But it's not a real galaxy, it's a part of a galaxy, a fragment of a galaxy. It's a tidal arm, it's either a spiral arm or a tidal tail, which might result perhaps from an interaction between two galaxies. We're going to go to Keck and look for H-alpha emission from this object to get a better idea of what's going on, and to, for the first time, identify a redshift for this foreground galaxy. Now, there's another possibility. As I just said, this might be a tidal tail. Tidal tails are the byproducts of mergers between two galaxies. And my colleague, Frank Hsu, got very interested in this, okay, our magnetic field detection. And his idea, he didn't like the idea of this 100 microgauss magnetic field being there because it's very hard to explain in terms of the dynamo theory. So his idea was that the pre-existing galaxies were normal. They had magnetic fields about 5 microgauss. And what happened is you had two spirals colliding, and the shock wave that's produced enhances the magnetic field. It's a radiative shock that enhances the magnetic field by a factor of 20 from 5 to 100 microgauss. And the whole thing works out pretty well. You need a merger velocity of 250 kilometers a second, which is certainly reasonable for the merger between two spirals. So here's a schematic diagram. You have these two galaxies colliding, a shock wave comes in, compresses the gas. I think it's a very elegant idea, but I don't think it's going to work, actually, because one of the problems is that the line of sight will be going through two spiral galaxies. You'll see two redshifts, not one. And one is all we observe. We don't really see two redshifts. But it's still an interesting idea. And then Frank, of course, came back with another idea, was perhaps what's colliding with this spiral is a gas-free elliptical. So the gas-free elliptical coming right through over here. It generates motions of the gas, okay? And it turns out the elliptical doesn't have to be very massive at all, about 10 to the 11 solar masses when you work it out and go through all the details. It has a profile of an isothermal sphere. It generates motions in the plane. These motions give rise to shocks, and the shocks can compress the magnetic field that we see here today. This is admittedly very speculative, and my colleague, Mike Norman, is going to try to calculate this for us to see whether it holds up. Of course, the big challenge in any of these theories is why the post-shock gas is so quiescent. Okay, whether we can really achieve that is an open question. Okay, so let me conclude by saying that this is the first measurement of a magnetic field at a redshift basically outside the Milky Way, and it results in a big surprise. The magnetic field is about 20 times what it is in the galaxy, and this is at a look-back time of 6.5 billion years, or another way to say it, we're looking at this giant magnetic field when this galaxy was only about 5 billion years old. And that puts a lot of stress on the dynamo theory. Remember, the dynamo theory is where magnetic fields get strengthened by differential rotation in a galaxy, winding up the fields, and the E-folding time is one galactic rotation period. So you really, to get up to about 100 microgauss, you've got to start off with a fairly strong field. As I said, the field is an average of a neutral gas with dimensions of at least 200 parsecs with a very low velocity dispersion. This is a challenge for any model. And we see no evidence. It's different from the usual places where we see strong magnetic fields, which are in regions of very high star formation. We don't see much evidence for star formation, which is associated. But again, this may be a selection effect. The consequences, as I said, the magnetic pressure is much higher than the self-gravity of the gas. And so the self-gravity of the gas cannot hold the magnetic field down. However, it could be confined by gravity due to stars in the central regions of an early type galaxy, or perhaps the B field could be enhanced by shocks generated by a merger. One of the byproducts of the merger idea is that the probability of seeing such an event is low. It's at most 1 to 2%, at best 3%, because it's equal to the merger. You have to take the merger fraction divided by the merger time and then multiply that by the duration of the time at which this shock stays in the galaxy. And there's some uncertainties in that, but it's still just a few percent. Of course, that doesn't mean it's wrong. Maybe we were lucky. Maybe a very weak and narrow magnetic field is the signature of a merger event. But I'll finally say, I don't have this on a slide, another interesting point about this is that one reason that the star formation rates in damped Lyman alpha systems may be low is that the gas is typically magnetized, okay? That most of the gas could be subcritical, and this could also help in understanding their low star formation rates. Okay, I'll end there, thank you. Sure.
Any questions? Yes, Ron.
So, discussing this last point about how to get the high magnetic field, try and do it by collision, as you just showed, the probability is really rather low. But in order to see this in the first place, yeah, that'll do. We won't ignore that. That'll do. You've got this radio source, otherwise you would never have seen the absorption. So why not shock the cloud by whacking it with the jet from the radio source?
It's too far away. The radio source has a redshift of 0.85. This guy's at a redshift of 0.69. My friend Jeff, though, could do it.
Yes, you commented about the low metallicity of your H1 cloud, where there's a magnetic field. Well, and then you concluded, you implied that there was no star formation. Yes, that's not necessarily the case. I mean, it just has to be the past history of star formation. No. So if the star formation occurs in bursts and then just stop, you still have a low metallicity. It's like, there's a dwarf galaxy, blue compact dwarfs that are as low as 2% of the sun, 1/50th. Like 1/18, for instance, and
remember,
of course, they have a huge burst star formation presently.
No.
Yeah,
I understand that, I agree, but it's not just the low metallicity, it's the low cooling rate of the gas that puts an upper limit to the star formation. Okay, and the cooling times are so short that you just can't shut down and keep the cooling rate like that. So I think it's the low cooling rate of the gas that also says that the concurrent star formation rate is very low.
I think you said that the magnetic field was very much larger than what you expected.
Yeah.
Yet, looking at the data that you showed us, if it had been 2 or 3 times weaker, you would not have been able to. How did you get the
chutzpah. That's the answer. I mean, the truth is, when we first started the experiment, we thought we could detect a 10 microgauss magnetic field, but then the noise was higher. Yeah, that's the answer. But yeah, So you're right. I mean, if we had known originally what that threshold was, sure, the only thing we could expect is a field that strong. That's exactly right.
Yeah, actually, on that point, I have a personal testimony to that point. It was about 2 years ago. I visited UCSD, and then after our talk, dinner, Art sat down with me and said, "Oh, Carl Hyles and I have this crazy idea to look for magnetic field in this system. You know, stop it nuts." And here we are. So that the lesson is never listen to theory. Still look. Yes, John.
I'm not an astronomer, so this will be a non-specialist question. You mentioned the grain photoelectric effect, where the photo-emitted electrons from a dust grain warm up the gas in its vicinity. We know from photoelectron spectroscopy that when a high-energy photon hits a solid, some of the energy that comes out is directly related to that transition, but a lot of the other energy in the electrons suffers losses inside the solid.
That's right.
And makes heat in the solid.
It heats the grains. That's right.
With different materials, that effect will probably be different.
Mm-hmm.
So how good is the grain photoelectric
That's a
effect?
very good question. It's been the person who I trust the most on this is Bruce Drain, who's calculated this. But to answer your question, he has used models, silicate grains and carbonaceous grains. And he feels pretty confident. Okay, now it's true, for the Milky Way, the grains are carbonaceous because we see this feature that's called the 2175 angstrom bump. And I don't have time to mention, in damp Lyman alpha system, there's no evidence for that. So here the grains that what we use were silicates because the reddening curve is consistent with the reddening curve that we see for the small Magellanic Cloud, where we think the dust is mainly silicates. So I'd say within a factor of a few, it's pretty good, to answer your question. Well, not several fold, no. Factor of a few. I'd say a factor of 2 or 3, yeah. Which is good enough for these arguments.